ژاپنی اون با برای اینقدر برای
Isn't that kind of problems? Okay, I hope everyone on Zoom can see me or see the screen. So let's get started today with the lecture. Since we're a little bit already quite behind due to all these delays. Okay, so quickly, today we're covering two algorithms, which finishes up basically all the algorithms that I wanted to cover in the main lectures. Some of the other algorithms are part of your projects and so on. So you'll explore some of them on your own. But before I do that, a couple announcements. Sorry, I think I have the wrong date on there. Sorry. Quiz will be held next Friday, right? Which is the 21st, not the 22nd. Sorry. 21st, not 22nd. The material covered on this quiz will be essentially these lectures and homeworks that cover these chapters 4, 5, and 7. And yeah, that's, sort of, if you read those chapters and are familiar with those chapters and the lectures and homeworks that cover those, you'll be fine for the test. The other thing I wanted to announce, and probably you've already seen this, but I just wanted to remind you that a teaching survey is available for the course. And since this is the first time we're teaching this course, and you're the first batch that is going through the QCQI certificate, your feedback will be really valuable to us in making this course better. And so I hope I'll hear from all of you on the course and what you liked and what you felt could be improved and so on. I always try to incorporate some aspects of the feedback in every course I teach in the semester after that. So that's something I've done many times in the past, whether it's like changing assignments, changing the way in which lectures are structured or so on. So yeah, all of your comments and feedback will be taken into account and used to improve the course. So please, I would appreciate it if you did that. Okay, and the last thing, which you all probably know already, and you've spent some time, I'm sure, forming your groups, but I just wanted to point out that the assignments for the project report and the code are now available on the Canvas, and they have rubrics also associated with them. So you can look at that. I haven't heard from a couple groups on their project title. So if you're still a little bit uncertain, make sure you talk to your group members, but also if you need any guidance, please contact me so I can suggest a topic for you. I should mention, just as a general guideline, those topics that I outlined in the project list, most of them, I think, have like tutorials and code available online, either via IBM itself or via other sources. So it's not supposed to be a complete, you start from zero and try to invent this, because obviously, it's meant to get you more familiar, first of all, with Qiskit and Python a little bit. But yeah, so I'm not expecting you to like completely code from scratch here. It is so that you learn a topic that's beyond what we can cover in this course and gives you a sense of like kind of how to research topics, how to write code for IBM and what the results look like and so on. I could have even, given some more topics, and maybe I will, like, even some of the algorithms that we have covered in the class. I've only had the time. I had originally thought I might cover the Qiskit implementations of Grover's algorithm or Qiskit implementation of, some of the other algorithms that we have talked about, but we haven't had time to do that. And I won't have time to do it next week either. So, if you want to pick one of those algorithms to implement, that's fine as well. So just suggest that to me and I'll let you know if it's okay, even if it's not on the approved list of projects that I put up there. Okay. All right. Any questions on this announcements and projects? Okay. All right. So I'm going to start by recalling what we finished in the last class, which is the QFT circuit. It said that if you take any input state given by these bits, by these qubits, and of course any superposition of them, of course, right? That's what quantum gives us. Then the output state, K0 through Kn minus 1, these qubits will be the quantum Fourier transform of the input state. Okay. And another way to represent that is that any basis state L transforms into this superposition over here. Okay. This is a product state, so it's not an entangled state, but it's a product state of many different superpositions, each of which is dependent on the input bits over here. Okay. And we saw that to construct it, though, all we need are Hadamard's and these controlled Rn gates. Rn, remember, was a rotation around the z-axis by 2 pi over 2 to the power n. So R sub n is a rotation around the z-axis of 2 pi divided by 2 to the power n. So, and that is this circuit over here. That's the QFT circuit. And let's talk a little bit about it because we were just finishing up at the end of last class. So I said this in words, but here I put it down, which is, so you can see from here, the Ln minus 1 qubit needs n gates, the next one needs n minus 1, and so on. And so if you sum up all of those gates, which is n plus n minus 1 plus so on up to 1, this is a very familiar arithmetic series I'm sure you've all seen, but even if not, you can sum it up by, for example, combining, say, the first term with the last term, that's n plus 1, the second term, n minus 1, with the second to last term, which is 2, so that's also n plus 1, and there are n over 2 such pairs. And therefore, this sum is n plus 1 times n over 2. Okay? So that's how you can sum it without, even if you didn't know arithmetic series before. All right, and then the QFT runtime, therefore, is just this n times n plus 1 over 2, which is order n squared. Okay, and remember, n is the number of qubits, which is logarithm of capital N. Remember, the Fourier transform, runs from over all the numbers, say like a C major chord, all the samples in that, which was digitized into like an n-bit string, and therefore that is log n the whole square. And this is what I promised that the QFT will do. It will give us the speed up, which is exponential, because the classical FFT runtime, which is the normal algorithm that we use on our computer to find the Fourier transform, is order n log n. So there's a speed up of log n additional over here, which is of course exponential speed up. Basically, you go from, say, if n is 44,000, logarithm of that is much smaller number. Okay, so you get that extra speed up in finding it. Okay, and this is just the. I like to always go to like a few number of qubits, just because, I did in the class like 2 qubit. This is the 4 qubit case, which shows you all the different gates, and you can see that it's indeed it follows that formula n times n plus 1, 4 times 3 divided by 2 number of gates. Leaving out the swap gates, sorry, but that's only an order n over 2 gates. So again, it's not that many. Okay, so then there's one more circuit that you should know, which is called the inverse QFT or IQFT, which undoes the QFT. And of course, if QFT is a unitary matrix, QFT dagger is thus the transpose conjugate of that. And since QFT itself was made up of these gates, right, all we have to do is reverse the order of the gates and take their dagger. Okay, and that does exactly this circuit over here. You see, I reverse the R2 over here and got a dagger and then H. And then the last line, as you can see, is Rn dagger, Rn minus 1 dagger, up to R1 dagger, and then up to R2 dagger, and then H. Okay, so that's, taking this and just undoing that, basically. Okay. All right, so a couple caveats about all of this. This sounds amazing, right? It's a exponential speed up over the classical algorithm, and you might wonder if, in that case, why aren't we just using QFT all the time? Well, let's discuss some of the caveats for that. Well, the first caveat is somewhat, at first may seem like a big problem, but I'll show you is not a huge problem. So as n, the number of qubits increases, we need to apply controlled rotation gates, OR gates, and the angles, as I said, go as 2 pi divided by 2 to the n. So if I take 1,000 bits, for example, which is quite common, right? I mean, you can get large numbers of samples of audio or any other file or whatever that you might have. Then we need to control this at a precision of 2 pi divided by 2 to the 1,000. So 2 to the 1,000 is a very, very small number, much smaller than, say, the precision of your normal computer. So even controlling this classically, controlling a rotation angle, for example, with a classical computer would be difficult. Okay. But it turns out there's a nice theorem. And essentially all I'm trying to say, I'm not going to go into what the theorem is stating. Here's a statement of the theorem if you're interested. But it says you can delete all the gates whose phase shift is less than some number. Okay. And which ones do you want to delete? Suppose you want a precision of 1%, then you delete all the gates whose angle is less than this, where k is given by this number. Okay. So it's just a way of saying that even if you don't want the exact QFT circuit, you get an approximation to the QFT circuit to precision, whatever you want, say 1%, say less than that, whatever. And by just deleting all those phase gates which are much smaller than a certain angle, okay, which are smaller than that angle. Okay. All right, so that's nice. So it simplifies the circuit a little bit. We don't need to go to like 1,000. If you want 1% precision, you just use this formula and delete all the gates that are less than that. The second caveat is actually a little bit more tricky. Okay? So after applying the QFT, the output state is in the superposition, which was given here, which is essentially what I'm saying is if I go back here, right at this point here, before I make any measurement, the output gate is in the superposition, the output state is in this superposition over here. Okay, and of course, if I apply some linear combination of these, that is meaning I make a superposition of all the possible basis states, then I get the coefficients of the DFT over here. So here, this is the output superposition over here. Okay, so this is the output superposition of the input coefficients. So upon measurement, though, it'll collapse, right? That's what happens on measurement. That whole thing is going to collapse to one of these states, some bit string, okay, out of this entire superposition whose probability is given by modulus squared of this coefficient. So you see the problem is that you're going to have to make the circuit and measure it many times to get like the actual coefficients, because to calculate the probabilities, because the probability is given by this DFT, but it's not the actual DFT itself that comes out in or the Fourier transform that comes out in the answers that we're getting over here. The answers are always going to be some binary representation of the states, and that's, and all we have is some probability. And this might require you to measure the QFT like millions of times to get a good histogram of all the DFT amplitudes. So you're kind of losing some of the speed up that you would have expected because you're having to do this DFT many times and then measure it and find the probability distribution to get the actual amplitudes. Okay, so that is not so nice. So in fact, what that says is that getting actual speed up over classical algorithms requires something just more clever than just simply measuring at the end. So it's only again for specific problems that we find that applying the QFT will give us a speed up. So let's talk about, is this point clear to everyone? Why there's, the speed up may not be as much as we expected? Maybe not. Maybe yes. Okay. All right. Let's talk about one problem where we can get such a speed up. Okay, so what we're doing now is the QFT basically becomes a subroutine. Okay, we did this with the QFT, but in fact, we won't normally use the QFT to find the Fourier transform because of these problems. Okay, Instead, the QFT will become a subroutine in other problems, and those other problems are phrased in such a way that the answer comes out such that in a way that represents the final answer, so to speak. Even collapsing it to one of those bit states is enough to give us the final answer. Okay. So our first problem is called phase estimation, and the problem statement is as follows: we are given a unitary matrix U and one eigenvector V. Okay. And we have to find the eigenvalue V, which is equal to e to the I theta. Okay. And just to remind you, we showed this briefly a couple of times, but an eigenvector of a matrix M satisfies M times ket lambda equals lambda times lambda, ket lambda. Okay. So this is, for example, if you take the X state, right? We know that the eigenstates of the X gate or the X unitary operator are the plus and the minus states. Okay. And those plus and minus states have eigenvalue plus one and minus one. So if you apply X to the plus state, you get plus times plus or plus one times plus. And if you apply X to the minus state, you get minus one times the minus state. So the state remains the same, except it's multiplied by a constant. Okay. And that constant or that value is called the eigenvalue. Okay. So here I use lambda just to denote both. Ket lambda is the eigenvector, which corresponds to having the eigenvalue lambda. So lambda is a number, complex number, but ket lambda is the eigenvector corresponding to that particular eigenvalue. Okay. So unitary matrices, it can be shown, have eigenvalues with unit norm, meaning lambda squared will be 1, which means lambda can always be written in the form e to the I theta. Okay. I won't go into the proof, it's fairly straightforward, but we don't need to worry about it. Okay, so that is our question or the problem that we're trying to solve. So since we're given the eigenvector V, and we're told the eigenvalues of the form V equal to I theta, we can now write the eigenvector equation for U. U times V equals e to the I theta ket V. Okay. And since U is an n by n matrix, capital N over n times n, we can write this as this matrix over here. So all the columns of all the elements in the first column vector, second column vector, up to the n minus 1 our nth column vector are over here, times the eigenvector, right? V0 up to Vn minus 1 equals e to the, sorry, sometimes I use j, sometimes I use I, just bear in mind, we typically use either I or j to represent the square root of minus 1. Okay. I try to avoid using j as a summation index for this reason, because sometimes I may use e to the I theta and sometimes e to the j theta. Okay, and this is again the eigenvector. So this is just the representation of this equation written out in matrix form. Okay, and now we can take any one of these rows, right? This is just matrix multiplication. I can take the first row, for example, multiply it by the column vector, and equate it to e to the j theta times the first element here. So, for example, I'll get u00 times v0 plus u01 times v1. Up to u0 n minus 1 times v1, adding all those together will give me e to the j theta times v0. Okay, and that is this equation over here. Okay? Just the first row multiplied by the column gives me this, and therefore I can immediately solve for e to the j theta. Okay. It's just this number divided by that. Okay, so how many calculations is that? So we take capital N multiplications, right? And capital N minus 1 additions, and then 1 division. Okay, so we have a total of 2n elementary operations. That is, the complexity of this is order capital N, which is of course 2 to the n, where n is the bits that represent the number capital N. Okay, so again, it's exponentially dependent on the total number of terms in the bits, or if you go back here, if you represented some matrix over n bit binary strings, then this is what the complexity comes from. Okay, there will be 2 to the n terms times 2 to the n terms in that matrix over. Okay, so now we come to the quantum solution. So the quantum solution is, we know the unitary matrix is working on an n-bit or n-qubit register. So we assume that we have n qubits, and let's assume for a minute that they are initialized in the eigenstate V. Okay, how we get to that is a question, separate question. We'll come to that, but let's just assume that we can do that. Then we call this the eigenstate register. Okay, and the unitary matrix, of course, can be viewed as some type of quantum gate. Okay, for example, if I know, I mean, you know, if I know exactly. So if I know exactly what U does to each bit state 0, 0, 0 up to 0 up to 1, 1, 1, I have a number that it maps that to, right? And therefore I can just use that truth table lookup and implement that in a reversible fashion. So something like so we know U acting on V is equal to something times V. So let's call that e to the I theta. Well, what this is saying is U, okay, acting on U can be written as some truth table, right? So I have all the numbers 0, 0, 0 up to 0 up to 1, 1, 1 up to 1, okay, and V is some one of these states, right? Basically, it's an eigenstate. It has to be in this form, and therefore, it can be written as some linear combination of these forms, right? So it's Vj times j. Oh, let's not use j. Let's use k. And I'm saying that as long as I know what U does to each one of these through a truth table, right? Because that's what U is, then I can just calculate what U acting on, what this V must be. I'm given the V, right? I'm already given what it is. So I just have to prepare some circuit that prepares the appropriate linear combination of these states. So V, you know, will have, you know, say it'll have some complex number V0 here, some complex number Vn minus 1 over here, and I just need to have a gate that applies these complex numbers or returns these complex numbers for that particular input state. Okay, so this is some classical circuit which we assume that we know how to implement on a classical computer. And once we have a classical truth table, we can apply that with a quantum computer by making that into a reversible circuit. Okay. Okay, so we have the n qubits that form the eigenstate register, which hold this eigenvector V. In addition, we're going to need m ancilla qubits or answer qubits that will hold the value of theta. Remember, we want the value of theta from all of this. And we will measure or find theta to m bits of precision. So we can't calculate it, obviously it's a real number, right? And we can't always calculate it to like all digits of precision that we want, but we can choose some number, say 30 bits of precision. That's already pretty good. If you're a floating point, then you can, you know, go up to 64 bits, whatever, you know. And we call this the eigenvalue register. Okay. All right. So now I claim that the circuit that I want is given by this circuit over here, and that this is the phase estimation circuit, which will result in this register over here. Sorry, this should be m minus 1, not n. Apologies. L0 up to Lm minus 1, and this register over here will hold the qubits up to, or will hold the answer theta up to m bits of precision. Okay. So let's prove that. Also, I should mention your textbook has a slightly different order of the output qubits, which is reversed relative to mine. And I don't know why they did that, because until now we've always been choosing the leftmost or the bottommost wire in your circuit is always the, to the left, right? It's the most significant bit. And the first qubit, the one at the top, is always the rightmost or least significant qubit. For some reason, they have interchanged that in this particular section of your textbook, which I find confusing. So I'm just using my notation over here. Okay. Although I may occasionally mess up M and N, so please bear that in mind. Okay, so, all right, so now what do we do? Okay, we start with the N qubits, which are, as I said, have already been initialized in the state V. Okay, I haven't told you how to do that, but we'll assume we can do that. Okay. And then we have the M qubits that we are starting with, and they are now, we're going to apply a Hadamard on them. Okay, so those M qubits have each been initialized into the plus state, which is denoted by this, of course, which is our favorite uniform superposition state. Okay. And so I just write that for simplicity. I'm going to omit this tensor product and all this stuff and just write it as 1 over square root 2 to the m, 0 plus 1, all of these 0 plus 1s times V, where V is the eigenstate register. Okay. Let's look at the rightmost qubit on the eigenvalue register, which would be, in this case, the top qubit, right, in our usual convention. Okay, and we're going to apply a controlled U gate with this qubit as the control and the eigenstate register as the target. That is this first control U, which will take this as the control and apply a U gate to the eigenvalue register, okay, which is controlled by this qubit over here in the ancilla register. Okay, so that's denoted by this operation, 1 over root 2, 0 plus 1 times V with a CU gate, controlled U gate. Well, what that is, we write it out as 0 times V, because when the control is in the 0 state, nothing happens to the V register. And then when the control is in the 1 state, I apply the U gate to the ancilla register. Well, U times V is e to the I theta times V. That's given to us. That's the definition of the eigenstate register. But now, basically, we can rewrite this in this form. So this becomes 0 plus e to the I theta 1 times V. So this is again an example of phase kickback. Okay. So the phase was really accumulated from the V register, but it has been kicked back into our input register because we prepared it in the uniform superposition. So this is again an example of the phase kickback identity. Okay. All right. So now we can continue like this. We go to the next most register, and this time we are not applying CU, we are applying CU squared. Okay. So when I do that by the exact same argument, I'm going to get 0 plus e to the 2I theta 1. Okay, so CU squared is just U applied twice. So that gives me U squared, and that's going to give me e to the 2I theta. Okay, so continuing in this fashion, after the mth qubit applies the final control U, and the final control U, we go by square. So it's like CU squared, CU fourth, CU eighth, so on and so forth, up to CU 2 to the m minus 1. Okay, so as many qubits as there are in the eigenvalue register, 2 to the m minus 1 is the number of squarings essentially of we're going to do m squarings of the CU register gate. Okay, and that gives me this phase. So it's just e to the I2 theta, e to the I4 theta, up to e to the I2 to the m minus 1 theta. Okay, and now I'll change our variable theta to be equal to 2 pi L, and if we find this L, we can simply multiply by 2 pi to obtain theta. And further, since 0 is lesser than theta, lesser than 2 pi, it's a phase after all, values of theta about 2 pi can simply be mapped back to a value between 0 to 2 pi. So that gives us that L must be between the values 0 and 1. Okay. So it's a So since L is a value between 0 and 1, we can express it as a binary number, which is 0 dot Lm minus 1, Lm minus 2 up to L1, L0, which I mean is just another way of saying I can represent it as, again, I'll recall the definition for a binary decimal number. So 0 point Lm minus 1, Lm minus 2 up to L1, L0 is just given as Lm minus 1 divided by 2 plus Lm minus 2 divided by 2 squared plus etc. up to L0 divided by 2 to the m. Okay. It's just like when I write, a decimal, like say 13.5, this is 1 times 10 plus 3 times 10 to the, so 10 to the 1, 10 to the 0 plus 5 times 10 to the minus 1, right? And so that's exactly what this is, except in binary. So it's Lm minus 1 times 2 to the power minus 1, Lm minus 2 to the power minus 2, plus L0 times 2 to the power minus 8. So same idea. We've seen this in the last class as well when we did the quantum Fourier transform. And so that's what, of course, we're going to take advantage of in this phase estimation circuit. Okay. Again, my notation is reverse and different than your textbook. So be careful when you're comparing. Okay, with this notation, and as I just said, I'm just recalling another fact, which is I just wrote that series, which had Lm minus 1 divided by 2 plus Lm minus 1 divided by 2 squared, etc. If I now multiply all of this by 2, right, now my Lm minus 1 comes in front of the decimal point because it's been multiplied by 2. Okay, so it moves, it's like multiplying by 10, a number that you multiply by 10. That will, if it has a decimal point, that number comes before the decimal, becomes, in front of the decimal point. Okay. And that's what this is. Similarly, 2 squared will be Ln minus 1, Ln minus 2 dot all the other digits of my binary expansion. And so on up to 2 to the m minus 1 will get me all the numbers except the last digit will remain behind the decimal point. Is this step clear to everyone? What I'm doing here, why this is true. Right, if I told you take 3.1415 and multiply by 10, that becomes 31.4159. And then if I multiply by 100, it's 314.159, etc. So that's what this is, except written in binary notation. And we can throw away all of the bits that are to the left of this. Why is that? Because every time, remember, I'm multiplying by e to the 2 pi I here. Going back again over here, this 2 pi, right, over here, theta was represented as 2 pi times a binary representation. And now I'm multiplying it by 2. That means any digits to the left of that decimal will be 2 pi times some number. So because L1 and L0 are binary, or even if they were integers, it wouldn't matter, because 2 pi times some integer, e to the 2 pi I times some integer is always 1. So therefore, I can throw away those digits because they only give me 1. Okay, so 2 pi I, they're just merely multiples of 2 pi I times 1, okay, which is equal to 1. Is that step clear to everyone? Why we can throw away all these digits to the left of the decimal point? Or binary decimal point. Everyone okay with that? Okay, so coming back to here, let's go through the steps again. I have this superposition, which I got by applying the controlled U gates. Each of these thetas was written as 2 pi times a binary representation, which is over here. sorry, that should be a 2 pi. This is a 2 pi. This is a 2 pi. Okay. And now I am writing that. Oh, I see. Sorry. So coming back here, what I was trying to say is if I throw away all these points over here, then maybe I should write this. Right. Let's write down the steps. Let's just look at the first. The first qubit was at 0 plus e to the I theta times 1. Okay. And I wrote that as at 0 plus e to the I pi times 0.L m minus 1. So that one remains as is. There's nothing happened to it. So that remains this. The next term was 0 plus e to the I 2 theta times 1. Okay, that is the first controlled u squared. So when I write this out now, is 0 plus e to the I 2 times 2 pi times 0.L1 Lm minus 1 up to L1 L naught, okay, times K1, okay, times 0 plus e to the I pi 0.L minus 1. And what I've just said, times K1, okay. What I've just said is this 2, when it multiplies out here, will bring the Lm minus 1 to the left of the decimal point, so I can throw it away. Okay. So what this gives me is 0 plus e to the I 2 pi times 0.Lm minus 2, Lm minus 3 up to L1, L1. So that is this term, and this term over here is 0 plus, as it remains the same. Right? That there is no change to that one. So that's 0.Lm minus 1, Lm minus 2 up to L1 times 1. So continuing in this fashion, each time I'm going to move one of these over to the left. One of these decimal, one of these bits will keep moving to the left and getting thrown away on each one. Okay. And so the final expression then will be written in this sort of way. This way, which is exactly what I wrote here. 0.Lm minus 1 up to L1 L naught. Then the next one starts at Lm minus 2. The next one will start at Lm minus 3, and so on up to 0.L naught, which is the last bit in the in the string. Okay. Okay. And so if I look at this, this is what will happen after all the controlled U gates are done. So that is our state after all the controlled U gates. And in our very first slide, we showed that the QFT, the quantum Fourier transform, what it does is it creates exactly this superposition, the exact same. So if I take this input state and apply the inverse quantum Fourier transform, I will get the state L, where L is all the bits in this bit string. So by taking the inverse quantum Fourier transform of this state, I'll undo this effect and come back to the state L, which L, remember, is in fact all the bits in the string that I want to calculate. which will be Lm minus 1 up to L1, L0. Yeah.
So there's like the first line, so like now we get that, like when we say now we get
Yeah.
that line right there. It's the first thing there with the 0.L naught.
Yeah.
Is that from applying the CU gate like M times or
Yeah, exactly. It applies it M times, correct. Or actually it's like Cu and then Cu squared and then Cu to the fourth
yeah.
up to M. Yeah, Cu to the power 2 to the M minus 1.
And that's what corresponds to that term.
Exactly, exactly. So yeah, that's right. So coming back here, all the way here. Yeah, right here. So yeah, this first one gives us the 0 point, yeah, the sorry, it's hard. There's so many terms. It's hard to keep them all straight, but
It's a lot to be tracked.
yeah, a lot to like retract each time. But yeah, so let me go back. Yeah, so this first, what I'm saying is up to here is just application of these controlled U gates, gives me a superposition which looks just like the quantum Fourier transform. And so if I apply the inverse quantum Fourier transform, I get back the basis state Lm minus 1 up to L0. That's the essential idea of that. You can see that here. Right here. So this, as you said, was the application of 2 to the M minus 1, and that gives me 0.L0, basically. That's the first term or the least significant bit in my binary expansion. And then this one will give me all of them, but because I know the L0 and L1 and so on, and by applying the inverse quantum Fourier transform, I will get now L0 up to Lm minus 1. So our state has become L0 up to Lm minus 1 in this way. Okay, so that's the end of the phase estimation circuit. That's it. You know, all it does is, because it's a very special problem, because what it does is it assumes that we have, so, oh, and finally, of course, at the end, we have got all the bits, L0, L1 up to Lm minus 1. We still need to calculate the phase. The original problem was to find theta, the phase. So that requires one more step, which is, you know, taking this 2 pi and then taking this Lm minus 1, dividing by 2 up to L0 divided by 2 to the M. So that's M additional divisions and additions. Okay, but those are order M in the number of elementary operations. So the total complexity of my circuit is M Hadamard's M controlled U to the power P gates and one inverse quantum Fourier transform. We already saw that the order of the quantum Fourier transform is order M squared, okay, where M is the number of qubits. So in total, M squared will dominate for large M, and therefore we'll get order M squared for the phase estimation circuit complexity. The classical solution, again, to recall, took order M, which is order 2 to the power n operation. So it depends on what M is, but M can be in general much smaller than M squared can be much smaller than 2 to the n, depending on M, the value of M and the value of N. Okay. There are a couple of small caveats. We have assumed we can create this V efficiently. So we have sort of ignored the whole, you know, complexity of how to create the V, the eigenvector V. Okay. And also we've assumed we can do these controlled U gates, which itself might require a lot of gates to construct. But this is kind of like that Oracle issue, right? It's kind of like saying, how many times do I have to query these gates U? You can try to phrase it in that way as well. Okay. Because you know, so that's another way to think about it, I guess. Yeah, I mean, again, this will form a subroutine in another algorithm. So maybe it's not too important at this point to worry about it. But yeah, this is kind of one of the main one of the applications of phases of the quantum Fourier transform. All right, we can extend it to multiple eigenstates. So we only took one eigenstate, but it's, there are other problems where, you may have multiple eigenstates and you can extend it. You can look at your section, the appropriate section in your textbook to see how that's done. It's not, I think, super important at this point. So I'll refer you to that. Okay, so if there are no more questions, I want to move on to the next algorithm. Unless you have questions for the PHYS stage. Okay. If you do, you can always come talk. Okay. So our next problem is to use something called modular exponentiation. And so first we'll start by denoting what modulo means. Modulo is a term for the remainder that's left behind after division. Okay. So it's usually denoted by mod. We saw this already in binary addition. So for example, I told you 1 plus 1 is equal to 0 modulo 2, right? So it's, if I take 1 plus 1, that's 2, but dividing by 2 gives me a remainder 0. So that's 0 again. So it's 0 modulo 2. And another example in daily life could be, the 12-hour clock, right? Which divides up the 24-hour day. So, if in military time we had said 1500 hours, that in normal regular language, we would call that 3 p.m. We said p.m. because we know it's in the afternoon, but if you just divide it by modulo 12, that would be just the number 3. Okay, so that's 3 o'clock. Okay. So that's another example. So in fact, I don't have time to tell you about all about the fascinating number theory, but just look up like modular arithmetic. There are some great videos by 3 Blue, 1 Brown. I think you all are familiar probably with him. So he has a nice video on modular arithmetic and the wheel arithmetic. So it's cool. So you can take a look at that. All right. So now what's modular exponentiation? This has some very powerful properties in the modular arithmetic. So we're going to talk about that. So it takes the powers of a number, some number, modulo some other number. So as an example, let's take 2 to the power 0 modulo 7. Okay. So 2 to the power 0 is 1, and 1 divided by 7 leaves behind a remainder 1. So this is 1 modulo 7. Okay. And then 2 to the power 1 is the number 2. 2 divided by 7 gives me the remainder 2, which is again then denoted as 2 mod 7. 2 to the 4 is 4 mod 7, right? Because again, 4 leaves behind the remainder 4. And now when we come to 2 to the 3, that's 8 modulo 7. But 8 then when divided by 7 leaves behind a remainder of 1. So that's equal to 1 modulo 7. That's why it's like a wheel or like a clock. Okay. So as we can divide up the entire number line, instead of lying on a straight line, it lies in a wheel going outward like this, where numbers like 8 will map back to 1, 4, and 2. So these will be, every number will essentially lie in the same sector of these of this number wheel, basically. So more, we can keep going, right? So we had 2 to the 3 mod 7 was 1 mod 7. 2 to the 4 is 16 mod 7, which gives me remainder 2 after division by 7. So that's 2 mod 7. 2 to the 5 mod 7 is again 4 mod 7. So you see the pattern, right? 1, 2, 4, 1, 2, 4 keeps repeating. Okay. And so this repeating pattern, it takes 3 times. And again, you can see it as you keep going. So you see that this has a period of 3. So that is between 1 and the next one, that takes 3 times to repeat itself. Okay. So that is the period or the order of the is the length of that repeating sequence, basically. Okay, so it's 1, 2, 4, that has a length 3. So the period of this modular exponentiation is called R, which is equal to 3 in our case. Is that clear to everyone? What this is? What the period is? Yes?
So that goes on forever.
Yeah, it goes on forever. Yeah. For the powers, of that. Okay. So I mean, if I take some other example, let's say powers of 3 modulo 10, we find a different pattern. For example, in this case, if you did it, you'd find 1, 3, 9, 7. So now my period is 4. Okay, so R equals 4. Remember, I'm taking powers. I'm not just taking every number on the number line. Of course, if I took every number on the number line, then I could get other answers. Like I could get, anything from say 0 up to 9. in this case. Any number divided by 10 will leave me reminders from 0 up to 9. Okay. But here I'm taking powers of a certain number. Taking 3 and I'm taking powers of it. 3 squared, 3 cubed, 3 to the 4th. And that has a certain different pattern, which as we have seen, the pattern is that you'll only get these numbers, 1, 3, 9, 7, with a period r equal to 4. Okay. And then the sequence will always start with 1 because any number a times it's to the power 0 is always 1. So, when I start with the powers of any number, positive integer a, then a to the 0 is always 1. And so the first number in that cycle is always 1 mod whatever number you're taking the modulus from. So in fact, you can show that the modular exponential ax mod n has a period r greater than 1 if and only if a and n are relatively prime. What that means is their greatest common divisor is always 1. If you remember from high school, greatest common divisor, right, for like two numbers is going to be found by a simple algorithm. It's called Euclid's algorithm, where you just take the two numbers, divide one by the other, and keep looking at the remainders, replacing the remainders, taking the division again until you get 1. And then in that process, you'll find one of them is the greatest common, one number will be the greatest common divisor. So that if that GCD is 1, it means A and N are relatively prime, meaning that they don't have any other factors in common except the prime factor, 1. Okay, and since the repeating sequence starts with 1, we can define this period R also as the smallest positive exponent R, such that a to the power R modulo n equals 1 mod n. Again, we can see this here in the example that I just showed you. You see that 2 to the 0 was 1 mod 7, 2 to the 1, 2 mod 7, 2 to the 2, 4 mod 7, and then 2 to the 3, remember R was equal to 3 for this case, 2 to the 3 modulo 7 was again 1 mod 7. So the smallest integer R such that a to the R modulo 7 is equal to 1 modulo 7 or modulo n, where n is where this a and n are relatively prime. You can see here 2 and 7 have no common factors except 1, right? So that's what it means. Okay, and so we see that in that case that a to the R modulo n always will become 1 modulo n. And since the numbers repeat every R powers, we could also say a to the x modulo n is equal to a to the R plus x modulo n. That's another way to define this order R of this. But the simpler way to think about it is just from this fact, a to the R modulo n must be equal to 1 modulo n. Okay, so this problem, it's called period of modular exponentiation, or more simply period finding or order finding. Okay, and it shows up in multiple cases. Why do we care? Really, so it's at the heart of many cryptographic protocols. That's why we care. Okay. It turns out like this is one of the most common ways, for example, to do Diffie-Hellman key exchange, which you might have heard about in communication. RSA, which is the other, I told you at the beginning of this course that RSA encryption can be broken by a quantum computer. So we'll see that the quantum solution to this is much faster than the classical solution of this problem. Okay. Any questions on this? That's why we care. Why period finding is important. The idea is, again, it's an invertible function issue. So I can give you some of the some of the numbers, and I can tell you that they have a certain property, but it's hard to, unless you know the numbers, to like actually find the order or something like that. Yeah. I'm kind of waving my hands here a little, but that's the basic idea. If I have time, we'll talk about it, but I don't. Okay. So we can calculate any one modular exponential quite easily. Finding the period for that, we can do it by using what's called the repeated squaring method. Okay. Or what I mean is we can just calculate that modular exponential, but finding this R is still very difficult because we have to calculate many of them, right? So remember, coming back here, we had to calculate for 2 for 2 mod 7, we had to calculate only 3 of them before we found out what the order was. But we still had to calculate 3, right? If you have a large n over here and a large number over here that you're squaring, that you're finding the powers of, you can imagine how many you would have to find till this pattern 1 mod 7 or 1 mod n repeats itself. Yes.
So if we're bringing the same number to like a certain power, we just keep increasing it by 1.
Yeah.
Once the pattern restarts again, we know for certain for like it doesn't matter what the number is, as long as it's the same number being watched the exponents, it's always going to just repeat.
Right. This is a famous theorem in number theory. I'm not going into that. Yes. Exactly. So once the pattern finds its, the period is found, it repeats. It constantly repeats. But finding this period beyond here I calculated like 3 of them and I got the answer. As soon as things become large, any of these numbers, if I make them large, now it's going to take me a much longer time to find that pattern. Okay. And we'll do with an example. Just imagine that you just had to find like one such modular exponential. Okay, here's one modular exponential. I want to find 91 to the power 43 modulo 131. Okay. It looks very complicated and difficult, right? We can calculate this faster than you would think. So let's go through how you might calculate this faster. You don't try to calculate 91 to the 43. Let's put it that way. Okay, because if you did that, we would be here forever. So instead, what we do is first we use the repeated squaring method. Everything becomes easier with binary, so to speak. So I represent 43 as a binary sequence. Okay. And this binary sequence is, you can just calculate it 101011, which can be represented again using our standard binary notation as 1 times 2 to the 5, which is 32, plus 0 times 16 plus 1 times 2 to the 3, which is 8, 1 times 2 to the 0 times 2 to the 4, 0 times 2 to the 2, which is 4, 1 times 2 to the 1, and then 1 times 2 to the 0. Okay, so those are just those numbers. So therefore, 91 to the 43 is broken up into these powers. Okay. 91 to the 1, 91 squared, 91 8, 91 32. Okay. And now we'll look at each of these individual guys, basically. 91 to the 1, 91 squared, 91 8, 91 32. We're going to find each of them individually. So let's look at that. 91 modulo 131 is simply 131. It's simply 91. Okay. 91 squared modulo 131, we do have to calculate it, but that's fairly easy on a calculator. 8281 modulo 131, that just has a remainder 28. Okay. 91 to the 4th looks a little bit more tricky, but we can write it as 91 squared the whole square. Okay. And that's just from the fact that 91 squared modulo 131 gives me a remainder 28. That's just 28 the whole squared modulo 130. Right? You can see that if you think about like what happens if I multiply two such things together. So 91 squared times 91 squared, each of them leaves behind a remainder 28. Therefore, the answer must be 28 times 28. So therefore, that's 28 squared modulo 130. And that's 784 modulo 131, which again on a calculator gives me 129 as a remainder. Okay, let's go to the next one. 91 to the power 8. That's again 91 power 4 squared. I already found out 91 4 is 129. So that's 129 squared modulo 131. And that's a slightly larger number, but still easy on a calculator. And that is remainder 4. Finally, we had to do 91 to the 16. Okay, straightforward. Again, it's just 4 squared modulo 131, which is 16. And 91 to the power 32. Same thing. Now that's equal to 16 squared modulo 131, which is 256 modulo 131, which is just 125. Okay. And that's all we need for our calculation because we broke it up into these 4 powers and we have all of their remainders now. Okay. So therefore, finalizing the step, that's basically I replace each of these by its remainder, 91 by its remainder, 91 squared by its remainder, 91 8 to the remainder, 91 32 to the remainder. Okay, now I have to do this calculation, which looks a little difficult, but again in pairs, if I take it in pairs, it becomes easy. So again, it's 28 times 91. Or I could just multiply it out on a calculator, whichever way you want to. So I just go through the step there. So that's 28 times 91 is 2548. I find that remainder, that's 59 relative to 131. And then I do that one, which is 236 modulo 131, which is 105 remainder. And then the last step is a slightly bigger number. But again, that's 13125, you can see, is going to be divisible by 131 with the 25 remainder. Okay, so that's our final answer. So 91 to the 43 modulo 131 gives me the number 25. In fact, I can do this much quicker if I use that modular wheel arithmetic that I was telling you about. It actually works out nicely. Okay, so this is the method. And remember, this is just to find one of these. And I have to find a whole bunch of them to find that pattern, to find that R. Okay, how many do I know? I don't know ahead of time how many I have to find. Okay, because there might be, I might have to search through a lot of them before I get the pattern R. I have no previous knowledge of what that R is. I'll just have to calculate as many as I can till hopefully some pattern reasserts itself. Okay. And so as you can see, we did so many multiplications and additions. You can show that it has complexity order n cubed in the number of bits, which is not bad. That's just one modular exponential. But unfortunately, finding that period, as I said, is large. It's for large n is very slow. So we need to calculate each of the modular exponentials. And in fact, there is no classical algorithm. So I can't tell you what the most efficient classical algorithm is. There is none, as far as we know, to find it. Okay. Other than this process. Okay, so sorry. This one, I thought I had this animated, but something went wrong. All right, so we're going to go through the quantum solution. But is the sort of the problem clear to everyone? What we're trying to solve? Yes.
Just to clarify, since we have that theorem where there's only a period r greater than 1 if they're relatively prime, are we just not solving the problem if they're not relatively prime?
Yeah, we don't care. Right, exactly. If they're not relatively prime, sometimes the answer can be very simple, really.
Mm-hmm.
Yeah, it's only the prime number wheels, as we say, that have these kind of cool properties, theorems and stuff. Okay, so first we're going to be assuming that we have a quantum gate U that performs modular multiplication. Okay, which is just, it's going to take U is going to take any number Y, which can be written as an n-bit string, and calculates A, Y mod M. Okay, because A and N are given to you. So you just calculate AY mod n. Okay. So Y is again an n-bit string, so it's restricted to the range 0 up to capital N minus 1. Okay, so let's start with, say, the state 1. Okay, then U0 acting on 1 will give me 1 modulo n, which is A to the 0 modulo n. Okay. Similarly, U to the power 1 acting on 1 will now give me A times Y times mod n, but Y is 1, therefore A mod n, which is A1 modulo n. Okay, next step, U squared is A squared modulo n. U to the R is A to the R modulo n. And remember, if R is the period, then A to the R modulo n is the same as A to the 0 modulo n, which is 1 mod n. Okay. So that's what U should give us when we repeatedly apply it to the state 1. Okay. So first, I'll go through the quantum solution in steps. The step 1 is we construct an eigenvector Vs of U. U is a unitary matrix. So we're going to construct an eigenvector Vs of this U, and we're going to show that its eigenvalue equals this number over here. So V sub S is some other number. Okay, doesn't matter for now, but and of course, it'll range over all possible values. But we'll show that the eigenvalue for this eigenvector is 2 pi I S divided by R, where R is the order that we're trying to find. Okay. Then I'm going to apply phase estimation to find the eigenvalue. And this has two substeps, 2a and 2b, which are somewhat complicated. which is how do we construct a controlled U gate, right? Because phase estimation required controlled U squared, control U to the fourth, etc. How do we get those gates? And finally, how do you construct the eigenvectors Vs as well? How do we actually make them? Okay. And then the final step is after I do all that, I'm going to get the eigenvalue e to the 2 pi s over r from this. So basically ignoring the 2 pi I, that's standard, I'll get s over r basically. How do I get, because remember the phase estimation gives me an m bit approximation to this eigenvalue, right? It's e to the I theta, and theta was found to m bits of precision in the phase estimation circuit. So how do I know from an m bit estimate or n bit estimate of s over r, how do I calculate r itself? That's the next question. Okay. We have to, given the eigenvalue s over r to m bits or n bits, you have to find r itself. Okay. And s, of course, will change each time when we make the measurement, as we'll see. Okay. So step 3 is really, it's the math of continued fractions. There are efficient classical algorithms to do this. So I'm going to skip this step for now, because that's like kind of math of continued fractions. And step 1 and 2 is what I'm going to discuss today. Yeah, especially we'll go into more detail on, I'm out of time. Okay. Maybe we have to pause it here. But okay, this is the algorithm, and I'll try to conclude this algorithm in the next class. Sorry, we got delayed due to all these technical stuff again. All right. Okay. Well, have a good weekend, everyone. I'll see you on Monday. Next week.